hoeveel werk we er dan van maken, dat valt misschien nog een beetje tegen.
Please mute yourself. So Helena, you're welcome to start.
Okay, but I have some. Sorry, I will see how to remove one of. Okay, yeah, it's good. Okay, good afternoon, everybody. Thank you, Joachim, first of all, for your invitation. I'm very happy and honored to present our result to all of you. And thank you for a kind introduction. So I'm working in the University of Rouen in Normandy. And today I will speak about the atomistic modeling based on the quasi-particle approach. It's a quite new model that we started to develop since maybe 10 years ago. And it opens the way to study the system at very large time and length scale. So I will show you some results from this method, but at the beginning, I will introduce the main assumption and a little bit history, how this method and why it was created. Sorry, just I would like to go down. First of all, I would like to thank all my colleagues, PhD student and postdoctoral student who participated in this work, and also Armen Kachirian, who contributed in the development of this method at the beginning. Just one picture from Rouen, from Normandy. As I say, I'm working in the University of Rouen in the group of physics of materials. And here you can see just a very nice air view of Rouen. It's very old and nice town with a very nice cathedral, as you can see here. So Rouen is situated approximately northwest direction from Paris, 150 kilometers. And this is an air view of our campus. And here you can see where is our laboratory is situated. I think many of you already visited Rouen and our laboratory. If not, it's informal invitation to come and to see our nice region and also our laboratory visited. So to start my talk, I would like first of all do some general description, and of course I would like to say that the understanding microstructure in many materials is critical because it governs many properties like mechanical properties, electrical properties, and thermal properties of engineered materials. This microstructure globally is created due to the many phase transformation which take place during elaboration or processing or aging materials. And this involve different kind of phase transformation like order disorder, phase separation of displacing phase transformation, which give us very complex microstructure. Here is just example, well-known rafting structure in nickel-based alloys when the ordering L12 phase emerged in the disordering matrix. And at present, now the phase field method becomes a very powerful tool to describe at mesoscale this kind of microstructure. However, as you know that many phenomena like segregation at grain boundaries, at different kind of defects, or just the structure of uncoherent interface, it's also very important to predict and to describe the properties of material. This is why in most of cases we go to a multi-scale approach in which we try to describe the material at different time and length scale. And as well as all this scale are quite developed at present time, for example, ab initio, molecular dynamic simulation, phase field modeling. However, the link between this different scale remains an open question. And today I would like to speak about this link which can exist between the mesoscopic and atomistic modeling. And especially, I would like to show at the beginning how we can use the phase field formalism to go to atomistic description of the system. In this case, we can go by two ways. We can go to the discrete description at atomic scale, in which we will consider the discrete lattice position and the position of the atoms which situated in the discrete position of the lattice, or we can go to some continuous approach, and mostly I will discuss mostly this method and this approach, which we call phase field crystal modeling, or from our side, it's a quasi-particle approach. I will explain what is the difference. And to obtain this approach, we can go from two ways. We can go directly from phase field and decrease the scale, and we can go from atomic density function, which is already works in atomistic scale, and go to some continuous description of the atomistic system. So the most main idea to create the methods or approach which be able to describe the system from atomistic scale to mesoscale, and to be able to describe the diffusion, for example, atoms, and to go to the very large time scale globally. To start, I would like to just to remember some main assumption which we are doing in the phase field modeling, and how it can be associated with the atomistic scale and mesoscopic scale. As you know, and it was explained recently by Professor Mellins, a very nice lecture about phase field modeling. The phase field modeling is based on the minimization of the free energy of the system, and it governed by the Landau-Kalatnikov relaxation equation, which is a linear equation with respect to the driving force. And this equation just gives us the possibility to describe the evolution of relaxation of the system near the phase transformation. For example, if we have the small fluctuation of the parameter psi, this equation gives us the kinetics or relaxation dynamics near this fluctuation. And this equation we can write in a different length scale. If we go to the microscopic description at the discrete lattice, we can associate this psi parameter with a probability function, and in this case we can describe the atomistic configuration using the probability function, which describes the probability to find atom at some given position. And if we introduce the free energy in mean field approximation, we can follow the development or evolution of this system at atomic scale, but at discrete lattice. From another side, if we go to mesoscopic description, it means that the simulation grid will be bigger than interatomic distance. We go to the continuous description. In this case, we forgot, I would like to say, about the atoms, and we work with the field. And in this case, the field will build the concentration or the order parameter, which will describe the coexistence of different phases in our alloys. The question is how to link these two descriptions. For example, if we are interested about the grain boundary structure, or if we would like to describe the displaced phase transformation at atomic scale, in this case, we cannot use this microscopic kinetic equation because the atoms is situated in some given position. So using the type on Zager microscopic kinetic equation, we are able only describe the order-disorder phase transition, but in the same symmetry of the crystal. From another side, if we do the phase field modeling, in this case, of course, we cannot have information about atomistic structure of this interface. This is why the question, and when we started to develop this method, it was how to combine this advantage from both method and to go some atomistic description, but at continuous scale. As I say, it can be done from the both sides. We can first go from phase field modeling and decrease the scale, and we can go from the atomistic approach and to go to some continuous scale. So just a few slides about this, we can say, historical development of this method. First of all, it was done coming from the phase field modeling, and is well known that the free energy in phase field can be divided into a path. First is the homogeneous free energy, which describe the different phases in coexistence, and another term which will be correspond to the interface between two phases. In the case, if we have some fluctuation in the system, the development of this fluctuation will be linked with the variation of this free energy, which we can represent in reciprocal space. And in this case, this variation can be written in this form, where this BK function will be very important, because it's clear that the minimization of this function delta F will be linked with the symmetry of this BK function. So when BK start to be negative and minima, the fluctuation will grow. In general case, this BK function can has a minima at a different position. For example, if this function is minima for k equals 0, we will observe the phase separation dynamic, as usually like spinodal decomposition. However, if the minima of this function is situated at given k, we will observe some periodic formation of precipitates, as you can see here, and we will have some K0 periodicity, or 2 pi divided by K0 periodicity of our in our system. So the minimization of this function, which give us the answer what kind of dynamic we will obtain during our kinetic phenomena, our kinetic process. And in 70s, when this Kahn-Hillard developed his theory, and Landau-Kalatnikov worked also on the dynamic of the instability of the fluctuation in the different kind of system, Brazovsky introduced some modification form of this free energy, as you can see here, to describe the crystallization in the system. And to obtain the crystallization, he needed to shift this BK function, as I said, now k equals 0. And in this case, the form of this BK function start to be like this. In minima, it's situated at given k. And here, use this free energy to describe the periodic formation of some concentration zone with a higher concentration zone, as you can see here. And this free energy will be at the beginning of the phase field crystal modeling, in which Ken Elder introduced in 2002 to describe the atomistic description of the system. But anyway, at the beginning, it was first introduction by Brazovsky, this free energy, which contains some supplementary term, K0, that gives the possibility to obtain some periodic distribution of the higher concentration zone. Then, approximately in the same period, Swift-Hohenberg interested about the convention phenomena. In convention phenomena, we know that if the two plates we will hit a different temperature, we observe some convention movement, which give us some the pattern formation, and this pattern formation can be described using again the Brazovsky free energy and Landau-Kalatnikov kinetic equation. Using this, Swift-Hohenberg describes the formation of this pattern structure. And we can see again that for some condition, we can obtain like stripe structure and some honeycomb structure, but in both cases, the distance between this higher concentration zone will be K0, or K0 is here, which introduced it in the free energy of the system. And in 2002, as I say just in the previous slide, Ken Elder had a very nice and very brilliant idea to say, if we will consider this higher concentration region like atoms, and then we will work with this concentration region like the atoms, it means that we can consider that atom move continuously in our space. The problem only in this approximation, if we go to the phase field formalism, that sometime we can obtain this stripe structure. What in the beginning was a problem in phase field crystal modeling, because a stripe structure is difficult to associate with some atomistic system. So this is why in our laboratory we will start to develop the like phase field crystal, but coming from the atomistic density function theory. In this case, in atomistic density function, the free energy can be written in mean field approximation, and we are working already in the atomic resolution. It means, as I say, we describe the configuration using the phase field probability function. And in this case, the chemical free energy of the system can be described like internal energy, which contains the interaction between the different sort of atoms, and the entropy term. It's possible also integrate the different other contribution, like elastic contribution or for example, magnetic contribution, etc. So solving the kinetic equation at atomic scale, we can obtain the evolution of the atom on the underlying discrete lattice. And here is just an illustration of this method. This is a formation of the carbide on the BCC crystal lattice in iron. In this case, the carbon diffuse in octahedral interstates of the BCC lattice, and we can obtain the formation of this carbide, and also some alignment and very nice microstructure formed by this carbon-rich zone. So, but in the 90s, Lonkin-Chen and Khachaturian started to develop this kind of approach, atomistic density function approach, and here obtain some very interesting results. They include in interaction potential two kinds of contribution. First of all, some finite range interaction, which was attraction, and long-range interaction, which in this case was a repulsive interaction in the Colombian form. So this is just Coulomb interaction in here. And solving the Onzager equation, then obtain that, like in phase field modeling, the precipitate course at the beginning we observe the coarsening of precipitates, but from some simulation time it can be seen that each precipitate becomes to be the same size, and they arrange to some periodic patterning. So this interesting result push us develop this like phase field crystal modeling, but coming from this description, which is atomistic description and based on the mean field approximation. So in this case, if we consider the simulation mesh, which is smaller than the distance between the atoms, interatomic distance, in this case, the atom normally could move in the continuous space, and of course, smaller the simulation grid, more freely the atom can move on this underlying lattice. The price to pay for this, of course, the atom becomes to be not the point like in mostly atomistic modeling, but some sphere, and this sphere will contain some number of simulation grid. This is why we introduced it new word fraton. Is means fraction of atom. It's not really fraction of atom. It's just the simulation grid which is belong to the atomic sphere. In this case, why we need to introduce this? Because if we start to our simulation, we should introduce the atomic density. In this case, it will be a little bit more complicated because atom will have the radius. So we should introduce the concentration of the simulation grid, which can construct some number of the atoms. For example, if we have 3 atoms, in our simulation, we should introduce the number of the grid, which will able to construct this 3 sphere with a given radius. So this is a difference between the discrete, normal, discrete description of the atomic system, and this continuous, we can say, description of the atomic configuration. So in this case, the probability function, it will be not the probability to find atom at some given position, it will be the probability this photon is inside of our atomic sphere. Another problem in the beginning, it was how in this case we can introduce the interaction between the atom, because if the atom is just the points, we usually accept that it will be interaction, point-point interaction at different distance, pair interaction on multi-body interaction, but anyway, we never consider the sphere. So in this case, if we go to this continuous space, we should introduce some additional interaction which will fix the size of the atom, and in this kind of interaction we call short-range interaction. The short-range interaction is introduced like the step function, as you can see here, and will give us the possibility to model the different size of the atom. So from one side, of course, maybe it's strange at the beginning, but from another side, it gives us this possibility to work with different atoms in size. And the second interaction, the long-range interaction, it means the interaction between the sphere of the atoms. It was introduced using the structural factor. I will not go in the description. If after we will have the discussion, I can explain why it can be linked with the diffraction, but just to say that long-range interaction, which will reproduce the crystal structure of a given material, which we would like to describe, can be linked with the structural factor of for the given symmetry of the crystal. Then solving the kinetic equation, which now will be follow the evolution of our photon, I would like to say, we can obtain the movement of the atom at some continuous scale. The free energy we keep like in mean field approximation, but interaction potential, as I say, in this case, will contain the two contribution, short range, long range interaction. And as I said, more important, the simulation grid will be smaller than the distance between neighboring atoms. So the reduced variable that we use, the time is measured in the unit of atomic migration time, the energy in the unit of kb T0, where T0 is a solidification temperature. The grid size is just the increment L. It's depend from the distance between the atoms, and usually we use the semi-implicit Fourier spectral method to solve our kinetic equation. So now we go to maybe more interesting part to show you how it works and what we can extract from this kind of modeling. Just if we introduce only short-range interaction, it means we will fix only the size of the atom without the given symmetry, and we will give some concentration of our photons. We will obtain the creation of some number of the atoms in some disordering state, and we can call this amorphous state or gas state. It depends from the density of these atoms. Now, if we will add the long-range interaction, in this case, for example, this is a self-ensembling of these photons to diamond structure. And in this case, as I say, we can link the long-range interaction with the structural factor. And the structural factor of for the diamond structure contains a product of the FCC to FCC structure with displacement one with respect to another by Y4, 1, 4, 1, 4, 1, 4. So we just introduce the symmetry of this crystal, and we can obtain the evolution of our system and growth of the diamond structure. It's possible also to work with a binary system. In this case, we can introduce the different radius of the atoms, and we should add the interaction between A and B atoms. And doing this, because in this case, the blunt system also produce like diamond structure, we also can show that using this kind of approach, we can go to quite complex crystal structure and describe the growth of the crystal with any symmetry. Finally, once we accept that the long-range interaction can be adjusted to the structural factor, the symmetry of any crystal, it can be describable using this approach. Now, to more concrete example, we were interested about the description of the grain boundary in alpha iron, in the BCC crystal of iron. In this case, we introduced the short-range interaction, which produces the size of the iron atom. The size will adjust it, of course, with respect to the first neighbor in the BCC lattice. And the long-range potential, in this case, is the BCC structure, and we can show that to obtain the BCC structure, we need only one minimal potential. We adjusted to the molecular dynamic simulation SK factor extracted from this work. So this is our adjustment, and in the red, it's the MD potential. And also to be sure that our potential reproduce some thermodynamic properties of materials, we calculated the bulk modulus and compare with the experimental measurement C for 4, C prime, and bulk modulus for alpha iron. So we can see that in spite that this potential is quite easy potential, I would like to quite simple potential, because it's only one minimal potential, as you can see here. It's asymmetric, but anyway, it's not too complicated function. And in spite of this, we can reproduce quite well, at least the elastic properties of materials. To obtain the creation of the grain boundary, in our case, we introduced two blocks of the BCC structure, which was simulated in the beginning. So in the beginning, we simulate the box with the BCC structure. We relax it after we cut some part of this box, and we rotate to a given direction, one with respect to other. Because in this case, we interested about the tilt grain boundaries alpha iron, so the angle it was 3.58, and then we put the liquid between. Liquid, it means that completely disordering fraton everywhere in all simulation grids. Doing this, after, if we decrease the temperature, the liquid start to solidify, and we obtain, for example, here, the creation of the grain boundary, as you can see here, and also some number of dislocation. So we can reproduce really the in 3D the formation of the dislocation and low angle grain boundaries. We did it for we modeled the different misorientation. As you can see here, it's a grain boundary 110 in alpha iron from 0 to 180. All these points correspond to the different misorientations that you can see here. And to be sure that in the beginning, because it was just at the beginning of development of this method, we relax our simulation by molecular dynamic, and we obtain exactly the same value which was obtained by in a paper of Chop, who uses pure molecular dynamic simulation, and T equals 0. It means in our case, we simulated the grain boundary as high temperature, T equals 0.9 T melting, and relaxing this configuration at low temperature, we obtain exactly the good behavior of the grain boundary energy at function of misorientation of this grain. Recently, we also applied this method to study the influence of the radius of the solid atom and the segregation phenomena. In this article, we consider mostly three sort of atom, X1, X2, and X3, with three different radius. One, R1, it was smaller than the radius of the iron. R2, it's approximately was the same, and R3 bigger than the radius of iron, which can be mimics the phosphorus, antimony, and tin. And we consider two kinds of grain boundary, the low angle grain boundary with theta equals 7.50 and 9.53, and the higher angle grain boundary 36 and 47. So we fitted our short-range interaction, as you can see here, which is different. It's normal because we will have the different size of the atom, and the short-range interaction which fit us this difference in size. And for the long-range interaction, we introduce for the iron-iron, of course, it's the BCC crystal, so it's one minimum potential, which is fitted, as I say, on the molecular dynamics simulation. And for the AB, we choose a completely separation. It means that it's unmissable system because its minima, it's situated at k equals 0. The result, it was quite interesting because we could reproduce the creation of the Cottrell atmosphere near, for example, the dislocation and low angle grain boundary. Here you can see, first of all, the grain boundary with presence of two edge dislocation for this grain boundary, and 3 dislocation if we increase the angle of misorientation. And the red color, red, yellow, and orange. Orange is difficult to see because it's approximately red. We can see the position of the solute atom and 3 different planes near the grain boundaries. And we can see that its atom is really create some clouds around the dislocation in both cases. If we compare this with Voronoi is volume of the atoms at the grain boundary, and which can be related to the elastic field, and the position of the atom, we really see that the interstitial solute atom decorate the dislocation core at the beginning, and also situated in the dilatation region near the grain boundary. So here you, in this picture, we can see that the atom smaller than iron, and in this picture, the atom is approximately the same size as iron atoms. For the higher angle grain boundary, what is interesting, there is two phenomena which can be interesting to underline. First of all, if we increase the size of the solute, we can see that it's more and more concentrated near the grain boundary. It means we will have some nude, what we call nude zone near the grain boundary if we work with solute, if we consider the solute atom much bigger than the iron atoms. In the case of the smaller atoms, we can see that it's distributed in some distance from the grain boundary, but in all these 3 situations, we see that we have some special configuration in which a solute atom will be integrated. We can show that the solute atom are located inside of the cupped trigonal prism, and this cupped trigonal prism is situated in the dilatation region of these higher angle grain boundaries. As well as now the computation, we can go to the very big simulation box. In our case, we are working usually we are working around 1023 cube simulation mesh. We can also describe the situation in the polycrystal materials. So here you can see the creation of the polycrystal materials. So in the beginning, we introduce some number of nucleus with a different misorientation, and can be, for example, texture orientation if we will rotate to some special direction, or it's just randomly introduce it. In this case, it just randomly introduced nucleus. And between the nucleus, we have the liquid, we put the liquid and we decrease the temperature, and during solidification, we obtain the creation of the grain boundary that you can see here. And then if we calculate the elastic field, we can also highlight the different compression and dilatation zone near the grain boundary, the existence of the dislocation, etc. So we can really describe the elastic field in one given polycrystal. Here, just I would like to show you how it happens if we increase the temperature and we have the recrystallization. We can see that, for example, one dislocation was emitted from grain boundary and it moved to the elastic field and annihilate to another grain boundaries. So this, as I say, this method opens the way to describe the dynamic and large time scale and large space scale, and give some idea and have to some idea about the segregation phenomena, polycrystalline materials, and also the interaction globally, different kind of defect with the solid atom. And here just we measured during the recrystallization phenomena, we measured the mean radius of the grain size as function of the time. In the case, if we are interested about the mechanical properties materials, it's already useful to calculate what happens at atomic scale if in some mechanical test. And in this case, as well as we have this simulation grid which can be adjusted with respect to the equilibrium position of the atoms or non-equilibrium position of the atoms, we can change the distance between the atoms and introduce intrinsically the applied stress in the system. For example, here we can see the equilibrium situation for the grain boundary with 46 degree and 36, and after under constraint. So it means that in this case, we apply the uniaxial stress in the x direction, and we can see that the answer of the system on this applied stress will be not evident, because, for example, here we will have the different units at the grain boundary, and if we apply the uniaxial stress, we obtain some deformation of the units, but not exactly the symmetric. It means that the different units will be deformed differently, and it can be linked with mechanical properties of materials. In this case, you can see that in the beginning, the grain boundary contains B, E, C units, as you can see here. And if we apply elastic stress, it means that only B units will be deformed, and C, we need really very strong applied uniaxial stress to deform these C units. So this can give some idea about what happens in polycrystalline materials if we apply this kind of deformation. We also tried the thesis with our colleague from KTH. We also try to understand the influence, the applied stress on the spinodal decomposition and iron chromium system. And this simulation, as you can see, the simulation when we apply the different kind of stress, for example, here it was tensile, compressive, shear stress, and for the different direction. So this, you can see the different color represents that iron and chromium atoms. And we can see that the answer of the system on the different applied stress, it's quite different. This is normal, but using this kind of modeling, we can, for example, predict the increasing of wavelengths if we apply the external stress. So this can be another interesting moment that this kind of prediction we can compare with the 3D atom probe analysis. And it was done in this case for iron chromium system. And in the left, you can see that wavelength measurement using the 3D atom probe analysis in the different direction under applied stress 231 in the experimental data, and in our case we applied 235 milliamperes, so it's very close. And in the up figure, you can see the experimental data from 3D atom probe analysis. We can see that chromium-rich region, and this is our simulation, and we can measure the evolution of this length scale of the spinal decomposition as function of the stress. In this case, it's for the given stress, but different direction, and we can see that, for example, there is some variation if we apply the stress in 001, 101, 111, or 112 direction. And if we compare the experimental result with our simulation, we can see that we can reproduce quite adequate the behavior, not exactly the value, this is a little bit bigger, but for example, applied stress 001 direction will distort much less our spinal wave than, for example, if we apply the stress in 112 direction. So this give us some confidence in our simulation to say that at least we can reproduce behavior, not maybe absolute value, but at least behavior of the system under applied stress in the binary system, as you can see here. We also started to develop this kind of approach to describe the segregation of carbon atom in polycrystal, of iron polycrystal, but now I will not go to this explanation. I prefer to show you some new result related to FCC-BCC phase transformation, as well as FCC-BCC phase transformation in the main transformation will induce the mechanical properties of steels. Many approach try to understand what happens during this kind of displacing phase transformation, and especially how the solid atoms interact with moving interface. So to calculate, to model the FCC-BCC phase transformation, we introduced two kinds of long-range potential. As I say, to describe the BCC structure, we need one minima potential, and we can show that to obtain the FCC structure, we need to introduce some supplementary minima. It's two minima potential, which can reproduce the or stabilize the equilibrium FCC structure. The latest parameter will choose FCC divided by BCC, it's around 1.22. And the thickness of this long-range interaction was chosen to reproduce elastic properties of both materials. For example, elastic properties in our simulation, the relation between the FCC and BCC structure show here, and experimental elastic constant reproduced here. So it's not exactly the same, but it's quite well coincidence between our simulation result and experimental data. So we use this kind of potential for the modeling that I will show just after. In the beginning, what is the interesting phenomena which can be obtained? We started the growth of the BCC nucleus in the FCC crystal. In this case, the initial configuration, it was a small BCC nucleus with a Kurdjumov-Sachs orientation relation. And during the growth, first of all, this nucleus becomes to be not spheroidal, ellipsoidal, as you can see here. And we observe the creation of the second variant of Kurdyumov-Zaks orientation relation. So the angle between these two variants, VR and V2, was calculated. It was around 71 degree, and the theory normally predicts 70. So what is interesting is that we are not introduced to something more. We really observe the appearance of this second variant of the BCC structure. And more interesting result we could obtain for the kappa iron system. With kappa iron system, it's unmixing system in which we observe the precipitation of the alpha particle with the BCC structure, and in kappa FCC matrix. And from experimental data, it was shown that this alpha particle contains multivariant structure. As you can see, there is a twin boundary that we can see here, and this is also the high resolution TIM images, which show that the alpha particle is not monovariant BCC structure, but a multivariant structure. And we try to understand how it produces this multivariant structure. So we did approximately the same kind of simulation that I showed just before. We introduced the small BCC nucleus with Kurdyumov-Zaks orientation relation, and then progressively we observe the formation of the multivariant structure. So in the beginning, we see that the nucleus becomes to be ellipsoidal, and the second variant is formed at the interface between the FCC and BCC phase. Finally, we obtain this kind of situation. So we have variant V2, V1, V2, and some perturbative zone around, which also contains some number of variants between the FCC and BCC. This simulation was done in the simulation box around 1024 cube. It corresponds approximately 43 cube nanometer. So to examine more clearly what happens in the twin boundary and the interface between the FCC and BCC phase, we did a more precise description of this situation. As well, we have the atomic position inside of the precipitates and at the interface. Here, for example, you can see some kink structure at the twin boundary, and also we observe that we have two kinds of interface. As usually, normally the twin interface is described using a reflection interface, which is just a reflection around some reflection plane, and also some isocell. Isocell, it means that there is a small shift, small displacement T1, one variant with respect to another. And if we look, if we study really, maybe here in the picture, it's not very clear, but we can see that we have two kinds of this this twin boundary. It means that in some zone we observe the reflection interface, and in some another isocell. So in most of cases we have this kink structure with intercalate the isocell and reflection interfaces. And during the propagation, what we observe that isocell is transformed to reflection. Reflection, it can go to isocell. It's accompanied by the stacking fold formation in 2-1-1 zone, and which results in the shift of the interface along the direction also -2-1-1, which is perpendicular to the twinned plane. At least what we observe in our situation. Also, we can separate our nucleus, not now nucleus, now it's really some precipitates of the BCC structure in the FCC matrix. And here you can see just really we select the atom which is belongs to the BCC precipitates. In this case, we can see that interface between the FCC and BCC can be described by some terrace. It's the 111 gamma or 011 plane of the BCC. So it's some intercalation of the terrace. And this terrace is also decorated around by screw dislocation, and this is a loops of the dislocation we can see here indicated in yellow, which corresponds this screw dislocation with the Burger's vector 1/2 110 gamma. So it's interesting because finally what we observe, this propagation between the FCC and BCC interface, it comes like in terrace, it propagates, and there is two kinds of dislocation. Finally, there is one part of the edge dislocation and two kinds of screw dislocation. To conclude that this is a screw dislocation, we calculate the displacement field, so the displacement of each atom, and you can see here, for example, give us a dislocation line and around the displacement of the atom, which indicates that we are near some screw dislocation, at least what we think. And after this analysis, we can conclude that we have this kind of situation. So our interface between the FCC and BCC, it can be considered like the terrace with some kink, as you can see here. And to propagate, we have two-step propagation. First of all, I would like to say that again, that we have this Burger's vector of this Shockley partial dislocation. We have two kinds of Shockley partial dislocation. You see in this direction and the perpendicular direction. And we have two kinds of the screw dislocation, B1 and B2. But globally, we can imagine, at least what we conclude from our modeling, that at the beginning, the Shockley partial dislocation with Burger's vector BP, which is noted here, produce the stacking fault, which will shift C plane to obtain ABB. It's well known that if you go to the 1-1 direction to FCC phase, we have ABC seconds of the dense plane, and to go to the BCC phase, we should do ABB. So to do this, normally what we observe that Shockley partial dislocation push the shift the C plane to transform ABC to ABAB. We produce, we can say, not ideal but HCP phase, and then that HCP phase should be compressed to obtain the BCC phase. And this compression, it's accompanied by the two screw dislocation. So in the beginning, we have some shift, and after screw dislocation, finally compress the HCP structure to produce the BCC one. And now we are working also in the framework of the thesis with Yuri Borg-Goma-Lima, which is now in our group. We started to study the plane interface. The plane interface, we also interesting because after we would like to understand the interaction of the solute atom with this kind of the interface. And here you can see the structure of the plane interface with Gringer-Trojan orientation relation. What we would like to underline that if we speak about FCC-BCC interface, it's not really something global. That really is all different orientation relation giving us very different crystal structure. And this will be completely, the propagation mechanism will be also very different. For example, here you can see the propagation of the plane interface. This is only the interface atom and BCC, which is indicated in the case of the Kurdjumov-Zaks orientation relation. Of course, it depends also with the habit plane, because the habit plane can be 100, 575, or 1-1, or 111 direction. So it will also change completely the structure of this kind of interface. And here we also, I would like to show this very fresh result, which comes last week. This is a Nishiyama-Weissermann orientation relation, where we have a very nice periodic plateau structure, some terrace structure, as you can see here. And what we started now to do is that we are interested, of course, to understand the mechanism of the propagation of this interface. You can see here that in this case of the Nishiyama-Weissermann, we see that the step higher, it's approximately 0.5 nanometer, and average terrace length, it's approximately between 1.5 nanometer. And if we do the slip vector analysis, in this case, it's a 575 FCC interface, we can obtain that you see in the blue and the yellow is a blue vector is a detection of the dislocation field. In fact, there is a dislocation line which is concentrated in this is the edge of the terrace. So everything happens in this edge of terrace. It means that we have some shear and also some which is governed by the screw dislocation. So I don't have, I see the time go, and if you have the question, I can we can discuss about. And just to show you the last result, but because we will try to now introduce the solute atom. In this case, we started to calculate the iron-carbon system. And in this case, we introduced the carbon-carbon repulsion, and iron-carbon was fitted with respect to the ab initio calculation. We just to take the first neighbor, second neighbor, etc. calculation, and we started and we tried to adjust our potential to this. This is iron-carbon repulsion. And we also introduce a different diffusion coefficient. For example, the carbon is diffused in this case approximately 3 times faster than the iron. And in this case, we studied the segregation phenomena at FCC-BCC grain boundary. This is a non-Kurdyumov-Zaks orientation relation. And you can see this progressively we have the enrichment of the carbon atom around this interface. It's go up to the approximately 10%. This is just a map during the a different time scale. So we see that in the beginning it's around 6, and in the end we obtain until 10. And if we do this for the Kurdyumov-Zaks orientation relation, the segregation is much smaller. And in this case, it corresponds nicely with the experimental data obtained by our PhD student, Olga Nakoniechna, who studied maybe 100 different tips across the FCC-BCC interface. And she confirmed that at Kurdyumov-Zaks orientation relation, the segregation of carbon atom is not very high. It's around 6 atomic percent. However, for the non-Kurdyumov-Zaks, when the interface is quite far from the Kurdyumov-Zaks orientation relation, the concentration of carbon atom can go up to 12%. So if, as again, I say that we are not exactly potential, which maybe completely fit the real situation, but at least we can predict that the non-Kurdyumov-Zaks orientation relation will absorb much bigger concentration, much more concentration of the carbon atom with respect to the non-Kurdyumov-Zaks orientation relationship. So this is just conclusion about the FCC-BCC interface with the carbon. So we can conclude the interface with non-Kurdyumov-Zaks orientation relation propagates faster than Kurdyumov-Zaks. The concentration of carbon non-Kurdyumov-Zaks it's around 12. And non-Kurdyumov-Zaks at 5-6. So to conclude, I would like to just to say that phase field approach is a very versatile approach, and we can work in the mesoscale as well. We can work in the atomistic scale in discrete lattice. We can work in atomistic scale in continuous lattice. Now this method start to be more and more developed in applied. So we can also associate the variable of the Landau-Kalatnikov kinetic equation with a different field, for example, with the atomic density field, with the composition, long-range order parameter, transformation strain, polarization, magnetization, Burger's vector, crack opening, etc. So I would like to say that, of course, when we speak about the phenomenological approach, it's not maybe give us not exactly the data like ab initio calculation, but it's give us the possibility to understand many phenomena in different field of application in different kind of materials. And just to last slide, where we are now, it means that we start to go, we try to go from atomistic to mesoscopic and mesoscopic to atomistic. I would like to say we are not completely linked together to method, but anyway, you see there is a small intersection anyway, which can work. And if we speak about the phase field crystal modeling or our quasi-particle approach, what we try to develop now to construct the database for the interaction atomic potential, which normally we would like to use as the experience in ab initio calculation. And of course, another problem is really link the time scale with this kind of atomistic phase field approach and phase field modeling, because as I say, the diffusion coefficient and the different parameters which will be scaled, the time scale is not completely understood and would like to say introduced in this kind of approach. So we start to go in both directions, but I hope it will be in the some next presentation, the two bridges will be more aligned to each other. So thank you for your attention, and I will be very glad to discuss with you.